So, once again, good morning and welcome to another session on probabilistic graphical models. Um, I I shared some documents on our Google Classroom. I don't know how many of you had time to review the the lecture or the yes. If you did, just type yes in the chat menu. And if you didn't do, just type no. If you did, type yes. If you didn't, type no. Nobody has typed. If you did, type yes. Oh, yeah. Some people did not even look at it at all. Not to even talk of. So Duper did. That's good. Uh, yes. Okay. Now the responses are coming. So I won't be asking you now, but we are going to discuss it together very quickly. There are some fundamentals which we just need uh, to master, to know as we go deep in the course. And let me share my screen. One of them is the concept of chain rule of probability. Um, even though in the course manual I mention it, but the need to really uh, elaborate on it uh, is one of the reasons why I'm devoting uh, a special discussion. So under this uh, section 2.7, you have advanced notes for readers with basic probability knowledge. And there, the mention was made regarding conditional probability tables, which we dealt with extensively last class. Today, we will focus on this other one, chain rule of probability, because you just need to uh, have a very good grasp of that concept. Of course, Bayes' theorem, we have handled that. So once we finish this today, then we can conveniently move to the next chapter, and then we'll see how far we'll be able to go as far as this course is concerned before the exam. Then, so I try to elaborate on this concept in the additional material that I shared so that you could possibly appreciate the uh, the chain rule, the concept of chain rule of probability. So our discussion will also look at the application to weather and linguistics. I know quite well that we have a mixed class, so that's one reason why we have to use applications from different areas. So, what do we actually mean when we talk about a chain rule? Of course, we've been talking about graphical models, and so when we draw graph, maybe you have this node, and then this influences this, and this influences this. Let's say this is A, B, C. So essentially, we are looking, chain rule helps to break down the probability of the joint distribution. So when we talk about the joint distribution, then we talk about the probability of A, B, C. This is joint. We've talked about joint probability before. But how do we now break this three probability of these three variables? No, the probability of these three variables happening together into series of simpler and conditional probabilities. So if we follow this graph, the chain rule helps us to now break this joint probability into the various components, to series of simpler and conditional probabilities. So going by this relationship or going by this flow of influence from A to B and then B to C. This is a very simple example. You could even have fairly more complex representation. So we could break this into first probability of A occurring times probability of B, but condition on A occurring, because that's the flow of influence. B will occur provided A has occurred, and then times probability of C, probability of C, given that A and B have occurred. So this is what we call chain rule of probability. So what it does simply is to look at joint probability, which is the probability of several events. In this case, 3 events occur at the same time, and then break these probabilities into simpler forms: marginal, conditional, conditional. So we will always use this as a way of helping to be able to look at multiple the probability of multiple events happening at the same time. So looking at our material, for instance, if we have x1, we have x2, we have x3, and all of them happen at the same time, then the chain rule, as I define it, is basically to look at the breakdown, is to break down the probability of the joint occurrence of the 3 events into these parts. So the first part, as you see, that's the diagram that I showed you. So you could see the diagram. This is x1. This is x1. Now let me use my. So this is, in this case, the same thing. You have x1, x2, x3. So the joint probability, which expresses the probability of the 3 of them occurring, would then be probability of x1 times probability of x2 occurring, given x2 occurring, given x1 times probability of x3 occurring, given x1 and x2. So the breaking down of this into this component parts is what we call the joint probability. You could have other, structure like this. Suppose you have x1, and this influences x2, and you have, let's say, this is the direction of the arrow, this is x3. If I want the joint probability of x1, x2, x3, then of course x1 is not conditioned on any variable, so it's probability of x1 times x2 is conditioned on x1. No. So I can have probability of x1 given, sorry, probability of x2 given x1. Now times what of x3? x3 is influenced by x1, not x2. So this will be probability of x3 given x1. So this is, can see the joint distribution here is different from here because this is the flow. So if you understand what I'm saying, type yes. And if you have a question, ask before we now move on to the next. I've not seen any response. I can see Timothy there. So that's good. So I can give you even more, complex relationship. You could have x1 influencing x2, and you have x1 influencing x3, and possibly x3 influencing x4. So you could find the joint probability of x1, x2, x3, x4. And based on that, you get the component part, right? So, of course, x1 is not being influenced by anyone. This is probability of x1. x2, that's being influenced by x1, probability of x2 given x1 times, for x3 is influenced by x1, so probability of x3 given x1 times x4 is influenced by x3 and x4, so that will be probability of x4 condition on the fact that x1 has occurred and x3 has occurred. So, and of course, you could have different form like that. So it's always advisable that you first of all, produce the graphical representation showing the relationship, and that helps you now to apply the chain rule. So the rule is, well simplified in if we are using the graph structure. So, like in the examples, each variable depends only on its parent. So this is x1 is the parent to x2. I think so this is the parent and x2 is the child. So x2 depends on its parent. x3 depends on its parent. x4 depends on its parent. And x3 also depends on its parent. That's the point being made here now. So the conditioning is not on everything before it. No, it's not on everything. So it's conditioned only on those, on the parents. So even here, you see x4 has two parents, x3 and x no, but the conditioning will not include x5, right? So if you have in a general expression, you have variables, n of them, x1, x2, x3, so n could be 2, could be 3, could be 4, n could be any number. So this is the general expression for the chain rule. You will notice the last one here is condition on n minus 1. So this is, you can easily see that in our discussion. So if you have 4 of them, then the last condition will be n minus 1, which will be 4 minus 1. So for those who are new to this concept, when we multiply, when we say x1 plus x2 plus x3, we can use the summation sign and say we are summing x, and we index by I and say I is starting from 1 to 3. So this is another, this is this is a more shorter way, using symbol to express this one. But what of if I'm talking about x1 times x2 times x3? I won't be able to use the summation. So what we use is the product sign, which is pi. Then I'll say xi, from 1 to 3. So for those who are new, just take note of, when you see this, it's simply saying you are finding the product of the xi's. When you see the summation, it means you are finding the sum of the xi's. So that's what you have here. So I can now apply the product, the product rule. So this is the product rule. So the parent I, or the parent of xi, will be determined from the graph. So if xi does not have a parent, like x1, then you are not conditioning it on anything. You are not conditioning it. Sorry. So if xi does not have a parent, then you cannot condition it on anything. Then it's simply the probability of xi. So you look at each variable's parent in the graph. So the parents, the variable's parent in the graph determines how you condition the variable. So take note of that. And why is this very useful? Yes, the whole idea actually is to reduce the complexity. Because if I decide to blow it up and I say probability of x1, then I write probability of x1 on x2 on x3 on x4. I write probability of x3 on x1, x2, x3, x4, probability of x4 on x1, x2, x3, x4. There will be so many redundant probabilities, So the chain rule, helps us to really be efficient. It reduces the complexity of the joint, distribution. So it allows us to build models, that are small, as you can see. It's more compact. So more compact now than if you have to look at all possible combinations and so on. So you have understandable pieces. You can easily relate the probabilities. So I can relate what is happening here in terms of the graph. I can relate what is happening to x3 in terms of his parent. I can relate x4 to x1 and x2, which are the parents. So you build a more compact model, and is one thing that we always encourage, that you make your model to be as simple as possible, taking note of only important variables. So we will talk about factorization. So what we have done exactly is what we consider as factorization. So factorization is nothing but breaking down, splitting, the joint probabilities in the probabilistic graphical models. So which means this expression that you see here is also considered as factors of this joint, probability distribution. So we are able to factorize. For those of you, at least you have knowledge of factorization in O level, is simply to break down expression that is of high high degree to very small one. So we can bring this to everyday knowledge, and we want to start from there. So imagine you are planning your day. I'm sure you did that this morning, and you check the weather, for instance. So the weather could be fine or maybe cloudy. Then you have to check the weather. That's a variable now, right? So you check the weather, then you decide whether to carry umbrella based on the weather. So if you have weather here, that's the first thing, and that will influence what happens to umbrella. So and again, if you are someone that your mood can always be influenced by weather, then the next reality will be about your mood for the day. So you have that. So, and your mood could depend on the weather and whether you carried umbrella. So if this is your mood will now have a chain of causes, because if the weather, uh, if it rained, if the weather was not too good for you, and you carried the umbrella, of course, uh, you know that you see the umbrella as a body, and the other discomfort it brings. So this is a typical everyday experience. So this is now in a graphical representation. And our interest now could be, we want to calculate the likelihood, the total likelihood that, uh, it will rain, and you carry umbrella, and of course, your mood will change. So you can be interested in that kind of doing probability. What is the probability that it will rain, and uh, you know, you carry umbrella, and the mood will be fine or the mood will be bad. You could also look at all possibilities. Maybe what I'm saying, I can make it a bit clearer. So you have here the weather, and the weather could be that it rains or not rain, and then the the next, whether you carry umbrella would depend. So you will depend on whether it rains or not. So let me simply say, instead of, okay, let me leave it this way. And then umbrella could be yes or no. So again, your mood would depend on what happens to weather and umbrella. Again, this could be mood could be, let's say, good or bad. Good or bad. So when we talk about the joint probability of weather, umbrella, and mood, then one probability that may interest us, we can look at all possible probabilities, but one is, we could look at probability that the weather, it rains, umbrella, yes, and then mood, good. This is one probability we could be interested in. Another one could be probability of joint probability that the weather is not, no rain, you carry umbrella, and then the mood is good. This is another one. You could also have another, so you could do all possible, uh, probabilities. So what helps us is the ability to be able to do the factorization, as you will see, in subsequent discussions. So if we now look at the weather-based example and we apply the chain rule of probability, you know, uh, to be able to understand the PGMs. So let's build a typical scenario, slightly, similar to what I've just done. So we are modeling probability of someone carrying umbrella, which means umbrella is yes, based on season and whether it rains. So this is season, this is rain, this is umbrella. And you could see the graphical structure. So this is S, that's the node. This is rain, that's the node. This is umbrella, that's node. Each of them, season is a variable which could be wet or dry. Rain is a variable which could be yes if it rains and no if it does not rain. And umbrella is also a binary outcome, which could be yes if you carry umbrella and no if no umbrella is carried. So you must be able to, in your modeling, of course, we talk of probabilistic graphical modeling. So you have to graph the relationship. You have to construct the graphical representation of the problem, and then that will lead to the computation of the probability. So this is simply saying that the season affects the rain, the likelihood of of rain. Whether it rains, affect likelihood of carrying umbrella. So this is what that graphical representation. And based on this graph now, we can apply the chain rule to decompose the joint relationship, the joint probability of season, rain, umbrella. So if we go by this, then this is probability. Applying the chain rule helps us to come up with this simple rule. So S does not have a parent, but rain, the parent is S. So we apply, that it becomes probability of rain given S. Umbrella here has a parent, which is rain. Now, you will notice in this case that season is not included. Yes, simply because the 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 season is not a direct no, it's not directly influencing you. No, but let's look at the hypothetical probabilities for the data. So let's say at least we know the probability that is it, the probability that the season is wet, 0.4, and the probability that it rain, given that the season is wet, is 0.8, and the probability of carrying umbrella, given that it rain, 0.9. So with that hypothetical, conditional probabilities, it's easy now to compute the probability that it is wet season and it rained and you carry umbrella. You simply substitute the values accordingly. So the value you have here is simply saying that you have 28.8% chance that all these three events will happen simultaneously. You have that the chance that the season will be wet and you will carry and it will rain and you will carry umbrella is 28.8%. So that tells you how likely these three events will occur at the same time. I repeat, that tells you how likely the three events will occur at the same time. So I've given reasons before why we usually do this in PGMs. And I've said one is the structure reduces, the complexity also reduces. And so there are some, for instance, you don't have to compute umbrella given season and rain, which I was trying to explain to you. So by just computing probability of umbrella given rain, you reduce the computational burden. Then your inference and reasoning is more efficient. Both are more efficient. And then you can apply this to forecasting. You can also make recommendations. So if I know that I'm in wet season, so I can also be able to know the likelihood that it will rain, and then I would need to carry umbrella. So what we have done here is also what you see the result using the R code. So I would like to stop here because of the other university meeting that I have. Any question before my colleagues take over. Any question? Oyeleye? Timothy?
No question, sir.
Kasaba, you came late.
Yes, sir. Sorry, sir. No question, sir.
Are you able to follow? Ganiyat?
I don't have questions.
Okay. So, Kafayat, are you able to take it over from here?
Good morning, sir.
Good morning, honey. How are you?
Hi, sir.
Uh,
I'll take it up, sir.
you are the one taking. Okay, good.
Yes, sir.
So you have the floor.
Okay, sir. Good morning, everyone.
Good morning, ma.
Sorry, was I saying anything?
Good morning, ma.
Oh, we didn't hear you. I thought you were not.
Sorry, I didn't know that I was muted.
Oh, sorry.
While he was calling me, I was answering, so I didn't know I was muted.
Okay.
So should I continue or you want to continue?
Maybe you would conclude the document.
You mean the exercise?
No,
Let me
no.
take the R part so that you can complete the exercise.
You mean the notes, lecture notes itself?
Yes.
Okay, okay.
Thank you. So I want to share my screen now. Okay, so good morning, everyone.
Good morning, ma.
Good morning, sir. So we are starting with the R codes now to illustrate what Prof has explained earlier to us. So I'll open my R now. This is just the practical exercise of what Prof has done so far. So to start with the first question earlier, that was a question on weather. That's the weather-based example. Yeah, where we have three variables: the season, rain, and umbrella. I want to calculate the likelihood of what happens as applying the R codes to solve this now. That is, imagine you are modeling the probability of someone carrying an umbrella based on the season and whether it rains. So using three variables, that's the rain, season, and umbrella. As Prof explained earlier, the season, you can either have wet season or dry season, and it might rain and it might not. You can decide to use umbrella or not. So let's look at practical examples in that aspect. Can you see my R code, please? Kindly confirm you can see my R.
Yes, ma'am. I come from my home.
Okay. All right, so we are given that the probability that the season is wet is 0.4. And the probability that it's rain given the season is wet, that's 0.9. with P of season is representing the probability that the season is wet and is defined as 0.4. You know, we are assigning, when you see anything before the less than and the hyphen symbol, we are assigning a value or an object to that particular word before the symbol, right? So we assign 0.4 to probability that the season is wet. Then the probability that there is rain, given that the season is wet, is this. So let's run the first line here. And this. And the probability that you decide to use umbrella, given its rain, that's 0.9. Now let's calculate the joint probability. By defining the joint probability, you know, we are multiplying, that's the product of the marginal probability and the conditional probabilities. In this case now, the marginal probability here is the probability that the season is wet. Why does this stand alone is that it has no parent. And the conditional probability is the probability of R given that the season is wet. And the probability of you deciding to use umbrella given that it rains. So let's run this. And then what do we have? You print the joint probability distribution. Then we have 0.288. So the practical example is as simple as that. Now, let's look at determining the structure of the scenarios using R. You need to install packages that are necessary. In this case, bnlearn as the essential package when it comes to determining the Bayesian network structure in R, and then the R graphics packages too. Then you can get it from this website, the bioconductor, and then you load the libraries of the packages that have been installed earlier. So I've already installed mine. Now let me load my packages. Right, so now let's look at the structure. Remember, we are talking about Bayesian networks. We are talking about DAG, which was done in the previous lectures. DAG is the directed acyclic graph. And to determine the structure, use the function model to network. It's a function in R to determine the Bayesian structure of a scenario. So let's run this and look at what we have. Okay. Now that I've run my function to say, give me the plot of this, then the graphics plot will bring out the plot for us. Plot of what? Plot of the DAG that I've defined earlier. And that's what this line is telling us. That's line 20. So we have the structure here. That's the rain depending on whether the season is wet, and the umbrella depending on whether it rains or not. All right, so moving forward to, let me go back to the note. So we've done it up to this point. Now let's look at the linguistic example in this part. I think, okay, did Prof treat this earlier? This part.
No, we've not gotten there.
Okay, has not gotten there. All right, so the scenario of using the part of speech tagging of a sentence. Let's consider the sentence, birds fly high. The part of speech in these sentences are just three. The first one being birds, that's noun. Then fly, which is verb, and then high, which is an adverb. So we want to compute the joint probability, or the, let's say, the likelihood that the verb is following the noun which is the bird. And then the adverb follows the verb, which is fly. Now, this is the joint probability. But like Prof mentioned earlier, it's better to determine the structure. This will make it easy for you to then use the chain rule to calculate this. Now, in this instance now, I'm saying that the verb follows the noun. Let me try and use it. So we have the noun, which is followed by the verb. This is the simple illustration of the Bayesian network for this, which is followed by the adverb. Now, the joint probability in this case, the parent variable here is the noun, which is this. That's the P probability that the first word is a noun, multiplied by the conditional probability that the second word is a verb, given that the preceding word is a noun, which is this. Multiplied by the conditional probability that the third word is an adverb, given that the preceding word is a verb. Now, given that we have this probability assigned to each of these, then by simply putting the values in this formula here, as a chain rule, then we obtain this. So is it clear to that point? Hello?
Yes,
Hello,
ma'am, it
is
is clear.
okay, thank you. So
Yes,
what
ma'am.
does that tell us? We have 0.72. This means that the probability that a noun is followed by a verb, as described in the scenario, then by an adverb, is 77.2% based on the sentence above. So why does this matter? Tagging models use this principle to predict part of speech. That's to tag your models to know the likelihood of a part of speech, how they are arranged in a sentence, and it's also resolved ambiguity. The word fly can be a noun or a verb, right? But the probability of surrounding tags helps to decide which of these is correct. It depends on how the sentence is being constructed. Now let's look at the R codes for this scenario. Okay, so these are the variables we have. We have the noun, which is the first word, the verb second, and the adverb. We already defined each of these variables. That's what we call the tags. Then each of the probability as given is defined like this. The first one is the probability that the first word is a noun. Then the probability that the second word is a verb, given that the first one or the one that precedes is a noun. Then the probability that the third word is an adverb, given that the one that precedes is a verb. So looking at the joint probability, this is the definition, right? It's just the product of the conditional probabilities and the marginal probability. So let's run each of these to see. And then we have 0.072. So from there, we move to the practical exercise, which I will leave for Ms. Oni to treat this with us. Right, if there's any question, please feel free to unmute and interrupt. So Ms. Oni, you have the floor. Thank you.
Okay, is there any question up to this stage? Okay, I'll share my screen. Okay, so we are going to be looking at 5 different examples, and we are going to be calculating it together. And maybe after I'm done with maybe the first or the second one, then I'll want us to also join in and let's do the remaining 3 together. I hope that's okay. So the first exercise is that okay, imagine a school where the school has 60% boys and 40% girls. Then 70% of the boys play football, while only 20% of the girls play football. Now, our question is, what is the probability that a randomly selected student is a girl and that she plays football? Then the second question is, what is the probability that a randomly selected student is a boy and he plays football? So we are going to calculate that. I'm going to show you how to be able to calculate that, and we are going to be using the chain rule. So I'm going to share a whiteboard. I'm going to share a whiteboard now. All right. So the first thing is that let's itemize all our nodes. That's variables. Let's itemize them. Then we'll continue the calculation. So the first thing we were given is the probability of the boys. No, we're given the percentage. Then it's left for us. I think Mrs. Kafaya has handled that part before. I don't know if it's this class. We were given 60%. So if we want to convert 60% to probability, please can we put it in the chat box what it's supposed to give us? We have 60%. What should that be? Somebody is saying something. 0.6, thank you. Then the 40% will be 0.4. So that's what we are going to be using. We're not going to be using the 60% and the 40%. Then we have these are the parent nodes. These have no parents, rather they have child. So we have the probability of the boys, then we have the probability of the girls. So according to our material, the probability of the boys in the school is 60%, is 0.6. As we have agreed, it will be 0.6. Then for the girls, it will be 0.4. Now our conditional probability that we have the boys, given that they can play football, that the boy plays football. We were told that it's 70%, that would be 0.7. That would be 0.7. And probability that we have a girl and she can play football. Now we're told it's 20%. So that would be 0.2. So we have written this down, and let's go into the calculation. The first question is, what's the probability that we have a girl and that she can play football? So we are going to have probability that we have a girl, comma, and she can play football. So it's going to be, we're going to have probability of girl times Nabil, are you saying something?
No, I'm following you.
Okay, times probability of girl given football. Good. And then we'll have 0.4 times 0.2. And that should give us what? If we are with our calculator, let's compute that and let me have an answer.
0.08.
0.08, correct. 0.08. Then if you have to calculate probability of selecting, sorry about that. Probability of selecting a boy and that the boy can play football, football. We are going to have probability of being a boy times probability of selecting a boy given that he can play football. So we are going to be having probability of a boy is 0.6. So we're going to be having 0.6 times probability of the boy given that he can play football is 0.7. So we are going to have times 0.7. And so we will have, what will be the answer?
Point 0.42.
Good, 0.42. So that's how to approach chain rule if you are faced with this kind of question. So we'll move to the second question. Let me show you. Okay, please go ahead, Tajudeen. Tajudeen, your hand is up.
Yeah, sorry, but please, I have a question.
Yeah, go ahead.
Prof mentioned earlier that we have the sum and the products.
Okay.
And can you please differentiate between the two? That's the product and the sum. Because the one we'll be using so far is the products. How about the sum? And then what is the difference between the sum and the products?
Okay. For normal probability rule, when you have and, you want to consider this feature and this feature, you're going to be using products. But when you are saying this feature or this feature, once it is or, it's going to be sum. But then there is something in PGM called sum product rule, in which we will get there. We have the sum product rule, we are going to get there. But if it's just a normal clarification between the product and sum, when you are dealing with and, so that there is a girl and that the girl can play football, you are going to multiply. But if there is a girl or a girl that can play football, something like that, then it's going to be sum. Do you understand a bit now?
Yes, mate, it's clear.
Okay. So the second question is this. We have the weather and the umbrella. So we have, suppose that probability of rain is 0.3. Then probability that traffic jam given rain is 0.6. Then probability that you're late given the traffic jam is 0.7. Then what's our question? Calculate the probability that it rains, that there is traffic jam, and then that you're late. So that's what we are going to be calculating now. Okay, so let's move to another board. Okay, first of all, let's try and draw the structure of how it should go. So probability that it rain, if there is rain, then this is the structure of traffic jam giving rain. This is how it should be. It means the traffic jam is depending on this. Rain is the parent node for the traffic jam. Then that you're late, given that there is a traffic jam. So this is what we are trying to represent. And then these are the numeric values. Probability that it rain is 0.3. Is 0.3. Then probability that there is traffic jam, given that it rains, is 0.6. Then probability that you get to the meeting late, given that there is traffic jam, is 0.7. So the question now is calculate the probability that it rains, that there is traffic jam, and then that you're late. That's the question. So we'll have probability that it rains times probability that there is traffic jam, given that it rains, times probability that you are late, given that there is traffic jam. And then we can just put the values now. It's much easier. So probability that it rains is 0.3. Then times probability that there's traffic jam, given that it rained, is 0.6. Then times probability that you are late, given that there's traffic jam, is 0.7. So at the end of the day, what do we have? I'm waiting for our response.
0.126.
Okay, beautiful. 0.126. 0.126. So that's our answer. Then we'll move to the third question. Let's quickly check the third question. So the third question is saying that, okay, for linguistic, this is a practical example for the linguistic. So we have a POS model that says probability of the determinant of a word being the determinant is 0.4. Then that the next word that will follow the determinant is a noun. That probability is 0.7. Then we have also the probability that the next word after the noun is a verb is 0.5. So then what is the probability of the tag sequence? This. So I won't be drawing this again. We already have a structure. So the determinant is the parent node. Then we have the noun depending on the determinant, and then the verb depending on the now, following the noun. So then we are asked to calculate this. I won't be sharing the whiteboard. We'll just follow what we have here. Let's follow what we have here. Okay, so let me just right here. So we now have probability of determinant, noun, and verb equals probability of the determinant times probability of the noun given the determinant and the probability of the verb given the noun. So based on what we have here, who will help us out? Let's just put in the figure, the numbers, the probabilities, and then let's multiply. One person, let's do it together. Who is ready? Okay, Mustafa. Oh, Surajuddin. I thought it was Surajuddin. So probability of the determinant will be
0.4
0.4
times
times
0.7
0.7 times
0.5.
0.5. And then we will now have a total of what?
0.140.
0.140. So we have 0.14. So that's the probability. Then the fourth exercise, I need somebody else. Okay. The fourth exercise is probability of ordering a pizza is 0.5. Then the probability that the pizza was delayed, given you have ordered, is 0.2. And the probability that customer complains, given that their order was delayed, is 0.9. Our question: what is the probability that an order is placed, it is delayed, and the customer complains? So first of all, we can draw the structure. So we know that we have, let's call the order pizza as 0, let's say 0. O. Then let's have the delay. Then let's have complaint as C. So this is the structure. And then we could see that the delay, this is delay given order, then this is complaint given the delay. So our formula will then be probability of, okay, should I continue here? Probability of order, comma, delay, comma, complaint equals to, who is going to help us out with this question? Who is helping us out? Do you want me to call names? Okay, I think we have to call names then. Oh, Yelaya Timothy.
Yes,
Oh,
ma'am.
Yelaya, are you in the class? Can
Yes.
we do this together?
Yes, ma'am.
Okay. So this is the joint probability. So let's split it. Let's put the formula.
Okay.
Can you go ahead?
Yes, ma'am. So it now be probability of 0.5.
No. Let's write the formula first before we put
The formula. So it now be probability of O multiplied by probability of D given O multiplied by probability of C given D.
Okay, beautiful. Then probability of C given D. Then we can now put our figures. So we have, go ahead, Timothy.
Okay. So it now be 0.5 multiplied by 0.2 multiplied by 0.9. So we now
Okay.
have 0.09.
0.09, correct. Thank you very much.
Yes, ma'am.
So we have 0.0.
Because it's not showing, ma'am.
It's not showing.
Yes, ma'am.
But okay. Oh, sorry. Okay, let's just do it. Let's do it here then.
Okay, yeah. Okay.
Okay. So it's showing.
Yes, ma'am.
All right. So that would be 0.09.
09.
All right. So the last question before I'll give the floor back to Ms. Kafaya. Okay, so this is a social media reaction. Probability that there is a post is 0.8. Probability that there is a like, given that you've already posted, is 0.6. And probability that is a comment, given that there is already a like, is 0.3. Our question is, what is the probability that a post is made, a post is liked, and a post is commented on? That is our question. So I need a female this time around to, we are going to draw the structures together, then write our joint distribution, our joint probability distribution, and then we put the probabilities and we do the calculation. We need a female. Who is going to volunteer? Ghanaians, would you want to volunteer? Ghanaian, are you in the class? Hello. Okay, let it. Okay, awesome.
Okay, so for that one.
Okay, so since we don't have a pre-done part, we can just move to the. But will you be able to remember the questions?
Yes,
I want to
I've
move to the
mentioned
whiteboard.
it. No problem.
Okay.
Yes.
Okay, so let's move to the whiteboard. Okay. So Dupe, go ahead.
So we start with representing those events.
Yes.
Like for the post, we can use P.
Yes. So that would be P.
Then an arrow, the like L.
Okay.
And the comment C.
Okay. C. Good.
So our question says, what is the probability that there is a post, it is like, and it is commented on?
Okay.
So that would be P, probability of post.
Probability of post.
Multiplied by.
No, let's put it this way first. Probability of post, comma, like.
Okay. Like.
Yes.
Comma C.
Comma, comment, yes. Equals.
Equal to.
Yes. Probability of
post.
Okay. Okay.
Multiplied by.
All right.
Probability of like giving post.
Probability of like giving post.
Post.
Okay.
Multiplied by. Probability of comment giving like.
Probability
Like
of comment.
Yeah.
Giving like. Good. Okay. Then.
So that will be equal to like. No, that's all. Then the next line will be we input the values for each.
Yes. So
that is
Probability of
0.8,
0.8.
yes,
Okay.
times 0.6
0.6. Okay.
times 0.3.
Times 0.3. Okay.
So that's equal to 0.144.
Yeah, you're correct. 0.144. 0.144. Okay. So I think three people were able to attempt it, but for the rest of the class, do we have any question? Even for those that we did it together, do we have any question before I would hand over to Ms. Kafaya? Do we
Actually, no
have any
question from my own end.
no question? You understand? Okay. Any other
Yeah.
person? Nabil, no question too.
Yes, yes.
Okay, it's clear. Okay. Okay, so thank you very much. Then over to you, Mrs. Kafaya. Hello, Mrs. Kafaya.
Yes. Thank you very much, Miss Oni.
Okay, all right.
Yes. So we are going to be looking at the same practical exercises for this time, practicalizing answering it using R software. So I'll share my screen now. All right, so the first question, can you see my screen, please? Miss Oni
Yes.
has already treated all the questions for us, but what we want to just do is solve them using R with few lines of codes, like we already did earlier. Just the values are different this time. So the first question is: a school has 60% boys, 40% girls, 70% of the boys play football, while only 20% of the girls play football. So what is the probability that a randomly selected student is a girl and play football or a boy and play football? So the line of code here, we need to define the probability that the student is a girl, which is given as 40%. They say we have 40% of girls. Then the probability that they play football, given she's a girl. That's hello. Is anyone saying anything? I can hear some voice. Is there any problem? Okay.
Nope.
So probability of this students that are boys in the class, that's 60%. Then the probability that they play football, given that the students are boys, that's 70%. So let's run this on our R and see what we have. So the first one here, probability that they are girls, probability that they play football, those that are girls, probability that they are boys, probability that they play football given they are boys. So I've already defined all that for my R console. Now I want to calculate the probability that they are girls given that they play football given they are girls, which is this line of code. That's the multiplication of the product of the marginal probability, as Miss Oni already illustrated for us while she was solving the questions for us. So multiplied by the conditional probability given that they are girls. That's what this line is telling us. And likewise, given that they are boys. This, then let's look at our answers. List the probability for us. Then we have 0.08 and 0.42. So did we get that? Okay, I assume yes. So the second question is the question on whether an umbrella has the probability that it rains is given as 30%. The probability that there's traffic given its range, which is 60%, and the probability that you are late to work or whatever the case, given that there is traffic, which is 70%. You want to calculate the probability that it rains, there's traffic jam, and you are late. Now, first of all, we need to define our values in R. The first one is probability that it rains, which is given as this. Probability that there's traffic, given that it's rain, given as this. So, and so on. Let's run this in R and see what we have. So you type in R as if you are calling it the way you are calling it out. Probability that it rains. You might decide to say P rain without the hyphen. Depends on what you want to define your values with. Doesn't have to be the same at this, but we only have to arrive at the same answer. So if I run all this together, we have 0.126. And the next question, linguistic part of speech tagging. The probability that they are given that the probability that the first word is a determiner, which is 0.4. Then the next word is a noun, given we already have the first word as a determiner is 0.7. And the third word is a verb, given we already have the second word as a noun, which is 0.5. Now we want to calculate the probability that the words are followed in that order. Then that's when we have this code to that scenario. The probability that the word is a determiner is this. The probability that the next word is a noun, given the determiner as the first, is defined as this, and so on and so on. Then what do we have here? We have 0.14. So remember when we talk about, when we say probability that the probability of a tag sequence or the word follows, or we are talking about likelihood. The likelihood that in a sentence, the first word is a determiner. And what's the likelihood that the word that will follow the determiner is a noun, and the word that will follow the noun is a verb? The likelihood that it exists that way is what we are calculating when we talk about probability in this case. Now, question 4. This is on pizza delivery. The probability that you order the pizza, which is 50%, the probability that your order is delayed, given that you ordered the pizza already, is this, and the probability that you complain, given that your given that your pizza is delayed, which is 90%. Now we want to calculate the probability that an order is placed, is delayed, and the customer complains in that order. What's the likelihood that this happens? So that's where we have this line of quotes as defined earlier. The probability that you ordered, the probability that it's delayed, and the probability that you lodge a complaint. Now, what's the likelihood? That's where we have the joint probability, which is the product of the marginal and conditional, like Ms. Oni explained earlier. So let's run this together and see what we have, which is 0.09. So the last one is on the probability that a post is made on social media, it is liked, and then it's commented on, given the scenario above. So the probability that you post on social media is given as 0.8 or 80%. The probability that that post is being liked is 60%. And then the probability that that post is being commented, and given that it is liked, is 30%. Then the probability that it happens in that order, the post is up on social media, it is liked, and then it is commented on, is this joint probability. Then what do we have? We have 0.144. So I believe by now your knowledge on R is widening and you'll be able to write these codes off and your exams. So thank you. Miss Annie, do you still have anything to say?
No, not at all.
Okay, thank you. So with this, we'll be ending the class and we meet next week again. And as regarding the physical tutorial or perhaps online tutorial, let us know which of these you prefer and your availability, because we have two departments. So one might work for the other and might not for the other. So please feel free to discuss within yourselves and then give us your opinion on the group. Thank you. So have a nice day.
Thank you, ma.